Hi everyone, this is a complete operating system video for placement. So I have covered all the important topics that are generally asked in the placements. Hope this video will help you to grasp the topic of operating system clearly. And all the links to notes and everything will be in the description, so you can check that out. What is an operating system? So let's start with that. An operating system is a layer of abstraction. What does that mean? That means that the operating system sits between the hardware that we have and the software. So it is a layer of abstraction so that the software can efficiently communicate with the hardware and use those resources efficiently. The operating system manages the system resources, so both the hardware and software. First kind of management is memory management, such as managing how much RAM you are providing to a process or a software. Second type of management is known as process management, where you manage how many processes you are running simultaneously and how you are switching between different processes, so no one process takes up all the memory and stop other processes. Why do we need an operating system? The operating system manages the resources for us, as we have seen in the last slide. Even if you have like nowadays 16 and 32 gigs of RAM is pretty common, and we have 4 to 6 core machine, 8 core machines. The operating system plays an important part in utilizing those hardware efficiently so that you can perform your day-to-day task easily and quickly. So that's why we need an operating system to utilize the system resources well. The operating system provides a platform to develop software, so people like us, software developers who write programs so that other people can do some stuff easily on their computer. So for them, the operating system provides an abstraction where it makes a lot of things easier, like we don't have to do most of the time manual memory management or manually managing how many cores our process is going to take or the software is going to take. Ease of usage, so the operating system can have softwares, and those softwares can run GUI, which is graphical user interface, so that users can easily interact with the system, and those who are not well versed with computers can also do their tasks like browsing the internet or playing games. Types of operating systems. So the first type is single process OS. A single process OS, as the name suggests, has a single processor and only one process at a particular time can be executed. The process that has to be executed is picked up from a queue known as a ready queue. So a ready queue in simple terms is a queue in which a process is waiting so it can get the CPU time, so it can process its task and run the instructions. We will learn about the ready queue more in the process scheduling section, which is coming ahead. Second type of operating system is batch OS. So in a batch OS, we have a single computer which is known as mainframe, which executes all the jobs. So the users will write instructions on a punch card and submit it to the computer operator. Then the computer operator will go ahead and execute those in the mainframe. Third type is multi-programming operating system. So in this, many of the programs are running simultaneously on a single processor. Many programs are running on a single processor. Only a single process will run at a time, so there will not be any parallel execution of programs. And if that process goes into IO, so it is like reading a file, in that case we will execute some other program. Meanwhile, the first program which we will running completes its IO, so we can do context switching between multiple programs. Fourth type is multitasking operating system. In this, we can execute multiple programs at the same time. Fifth one is distributed operating system. So in this, we have multiple CPUs which are serving multiple real-time users, and to those users that system looks like it is just one computer, but in actual reality there are multiple computers in the background. Sixth one is a real-time operating system. So in real-time operating system, we have time critical processes like in satellites or in rockets. Now let's talk about the kernel. So the kernel is the core component of the operating system, and it is also known as the brain of the operating system. It provides and manages the computer resources. It does the process management, memory management, and it contains the device drivers. So let's say you are plugging in your keyboard. So the way the operating system knows that you are plugging in a keyboard is through drivers. So the device drivers are inside the kernel. The kernel also handles system calls. We will look at system calls in the upcoming slides. Let's start with system call now. So system calls are used to interact with the kernel. So it is a layer of abstraction or an interface between the application and the kernel, through which the applications can perform various tasks like opening a file using the open system call. So system call in higher level is just a function, just like a function call. So you are making a function call to do something. Here is a list of system calls. I have provided the link. You can check it in the description as well. So now let's talk about some key terms about memory. So we have two types of memory. The first one is random access memory, also known as RAM. So it is a temporary memory. As soon as the system switches on, we get a RAM, and when we switch off our system, there is no direct supply of power. The RAM is emptied. So it is a temporary memory, and it contains the data of all the running application. So let's say you are running a browser, so that browser is residing inside your RAM. Second type of memory is read-only memory, which stores the information permanently. So now the question arises, we know what does a RAM contains. So RAM contains the running applications, but what does the ROM contains? Let's try to answer that question. So first thing that the ROM contains is a BIOS, basic input and output system. So BIOS is a software responsible for power on self-test and makes it the very first software to run when a computer is started. So we will talk about the power on self-test. What is that? So we have a bootstrap loader or a bootloader inside the ROM. The bootloader reads the hard drive boot sector. So there is a boot sector inside the hard drive, and it continues to load the operating system. It sees all the entries that we have, like let's say we are dual booting our computer and we have Windows and some Linux operating system installed. So it will list all those entries there. So the ROM also contains CMOS or CMOS. So the CMOS allows you to change various settings like the boot device, etc. So you can go into your BIOS and change which boot device should come first, like a pen drive if you want to install an operating system. Also the CMOS contains information like date and time. So if you at some time open the BIOS, you see that there is a date and time there. So how that is stored is inside a CMOS. So this is the picture of CMOS. That's how a computer knows the current time. So the CMOS is having like this coin shaped battery which is always powered on, and since the computer system might not have power throughout the day. Now let's see how is this information stored in CMOS. So there is a battery powered memory state that allows the system to keep track of date and time when the system is powered off. So like we have a battery here. Using that we keep track of the time, date and other settings. Note that even though we have this time and date inside the CMOS, but the more accurate date you get it from the internet. So once the PC boots up and you are connected to the internet, the operating system fetches time from an online source. So that is more accurate as compared to the CMOS, because the CMOS battery can die and that can make your operating system time wrong. Now let's talk about the power on self-test. So we saw that the power on self-test was executed by the BIOS. So it is a test that verifies that all the hardware is working properly or not, like the hard drive is not corrupt and the RAM is working fine, it is plugged well into the system. Now we start with a very important question which is asked widely in interviews. So this is, how does an operating system load? So here I have mentioned a few steps and we will go on in all these steps by detail. And note that I am discussing the steps of Linux, how Linux works while booting. The first one we have is BIOS. So the BIOS initializes the hardware and runs post. So post is power on self-test as we saw it. So the first step is BIOS. Second one is the bootloader. So bootloader loads important information like date, time, which is stored inside CMOS. So the bootloader also shows us the operating system entries, and Grub is one of the famous bootloader for Linux. So at this point the bootloader loads the kernel image and the initial RAM, which is also known as init RAM-fs disk, into the memory. So it loads all of that into the main memory, that is RAM. So the kernel here initializes and configure the computer's memory, and it also configures the hardware attached. Like we talked that the kernel has the device drivers. So all those things like your mouse, keyboard, everything is identified using those device drivers. There are some display managers which are loaded by the kernel, like GDM we have, which is the GNOME display manager. Next one is initramfs. So the initramfs mounts the root file system, and it also loads the required device drivers. So once the initramfs finished its first step, it is removed from the RAM since we no longer need it. So mounting is the process of attaching like an external storage to our computer. It can be a USB, hard disk or any other thing. We will be talking about mounting in the upcoming section. Next one is init system. So this is a process which starts some other processes. Like you might might configure your system to run any program. Let's say you configure your system that it runs Discord every time you open your computer. So the init system is responsible to load Discord, or you might be using some other services. Let's say you are using a VPN. So the init system, you can configure it to load that VPN every time you start the computer. So once the work of init system is done, this is also cleaned from the main memory. Next one is shell. So shell is a program that takes the command from the user and it executes it and display the output to the user. So it is like a REPL, read when print loop. So it reads the command from the user, evaluates it, and then print, and then continue that process. So a few example of shells are bash, zesh, and fish. Now there is a Windows system as well. So the Windows system is responsible for handling the windows and painting the windows on the screen. Like if we open, let's say, the terminal, where on the screen will it show up, and if you move a window, how is that configured? So all those things are managed by the Windows system. A few example of Windows system is Xorg and VLAN. Interrupts. So interrupts are signal emitted by the hardware or either the software when a process need immediate attention. Let's say we plug in a keyboard. So interrupt is sent and to the operating system to tell it that we have connected a keyboard. If there was no interrupt and there was no way of signaling that, we would have to wait for the operating system to pick up this that a keyboard was connected, and there would be a huge delay. So we have an interrupt handler inside the operating system. The work of the interrupt handler is that it prioritizes all the interrupts when to execute, and it maintains a queue inside the operating system to keep track in which order those interrupts should be handled. Let's talk about why do we need interrupts. The first use case is preemptive scheduling. So what do we mean by preemptive scheduling is that, let's say we are running one process, so the ability to pause that process and then run some other high priority process. Basically we are pausing a process and running some other process, and once that process is done, we can resume the process. So that is known as preemptive scheduling. Interrupts also helps the operating system to handle different conditions when the program can't proceed further. So that can be like a page fault, or maybe some exception occurring, or maybe there is some memory corruption of that program. Interrupts are also needed to make the system calls. So there is a context switching between the user space and the kernel space, which we will talk about later. Handle signals from the external devices, as we have talked, like connecting a keyboard or a mouse. Now let's see the type of interrupts. First one is hardware interrupts. So the signals generated by the external hardware devices. So let's say we are pressing any key on our keyboard, so that creates a signal which is an interrupt itself. So that those types of interrupts which comes from hardware are known as hardware interrupts. So these interrupts can arrive asynchronously. The meaning of asynchronously here is that they can preempt the normal execution. Let's say we had a program running and then we press escape or alt F4 to quit it. So those are preemptive. Like we can stop the current process, execute this interrupt first, and then continue with it. Next type of interrupts is software interrupts. Software interrupts are also known as traps. These are mostly generated because of some abnormal condition, mostly when we are invoking system call, but some other conditions can be an error occurring or an exception occurring, something like that. So these are synchronous. That means the process can continue the execution, and whenever this interrupt is ready to be executed by the interrupt handler, it invokes it. Now let's see how interrupts and exceptions are handled. So first we stop the execution of the current program, which is also known as context switching. Then the interrupt handler comes into the picture and it starts the execution of the interrupt from the queue. So as we talked about, the interrupt handler maintains a queue. It picks up some interrupt from that queue and start executing that process. So a process simply is a program that is in execution. A program can be some code, any binary file, memory layout of a process. So in this section we will learn how the process is stored in the memory. So there are mainly 4 sections: stack, heap, data, and text section. Let's look at them in detail. First of all, the stack section. The stack section stores the local variables, function calls, and return address. And as we can see in this diagram, that the stack and the heap section grows in opposite direction. The reason for this opposite direction is that we can have efficient use of memory. So let's say the heap was here and the stack was on top of it, so heap couldn't grow. As a result, we would not be using the memory efficiently. So what we do is we keep stack on the top and heap wherever on the bottom we have space, and then we grow them in opposite direction, so the leftover memory can be used efficiently. Heap section. So the heap section provide the dynamic memory. So let's say we are allocating a dynamic array, So that will be stored inside the heap section. Now the data section. The data section contains all the global variables and static local variables. Text section. So the text section contains all the instructions. So that is generally the code we write, and then that is converted into the assembly language, and those instructions are inside the text section. And there are constants and macros as well in the text section. So the text section is read only and can also be used by some other process. So if we have some code running and we want to run other copy of that code, we can say share the text section. Life cycle of a process. So in this section we will see how a process goes through different cycles and what all state it can be in. First one is the new state. So in the new state, the program is loaded from the secondary memory like a hard drive, and it is moved to the main memory, which is the RAM. So this is what the first step is. Second state is a ready state. So once the process is in new state, then it goes into the ready state. So inside the ready state, the process is ready for the CPU and is waiting for the CPU to schedule it. And the processes that are in the ready state are maintained in a queue, also known as a ready queue. After the ready state, we have the running state. So in the running state, the CPU is doing the computation and running all the instructions. So we can see that we had a ready state here, and then we dispatch, then we have it in the running state. Fourth one is wait and block. So this is right here. So whenever a process want to wait for IO, like it has to read some file from the hard drive, or it have to make a network call to access some APIs. So in that case, the process will go into the wait or block state. And once the IO is done or the network call is finished, what we do is we send the process again into the ready state. Fifth one is terminated state. So the process is done and it gets removed from the primary memory. Next is suspended ready. So in this case, the process was initially in the ready state and then it was swapped out of the main memory. The reason can be anything, like there is not enough space in the main memory and some other high priority process wants to enter the main memory. So in that case, we can send the process to suspended ready state, and once that state is finished, we have memory in the main memory. Then what we can do is we can resume that suspended ready and it will come back to ready state again. Seventh is suspended wait. So the suspended wait is somewhat similar to the suspended ready state. So in this, what happens is if a process is doing some IO and then let's say we can't finish the IO right now, we have some other priority task that want to do IO. So what we want to do is we will send the process into the suspended wait state and then we can later on resume it. So after the suspended wait state, the process goes into the suspended ready state and then it will go into the ready state. Next up is schedulers. So the schedulers handles how a process can move from one state to another, like when we should swap something out of the memory, or when we should move something from suspended ready to suspended to ready state, stuff like that. And the main part of the scheduler is to move a process from the ready state to a running state where the CPU can execute the instructions. So there are different types of schedulers. First type of scheduler is the long term scheduler. So what it does is it moves the process from the new state where it was loaded inside the RAM to the ready state where it is finally ready to execute and waiting for the CPU to acquire it. And the long-term scheduler also decides how many process should be in the ready queue, since the ready queue space is limited. Next up is a short-term scheduler. So the short-term scheduler moves a process from ready state and into the running state and vice versa. So if we want to move the process from the running state back into the ready state, that is also done by the short-term scheduler. Third one is medium-term scheduler. So this one does the suspension part, like there was suspension ready and suspension wait. So these are handled by medium-term scheduler. Now the concepts related to processes. First one is degree of multiprogramming. So degree of multiprogramming is the number of processes that can be inside the ready queue at once. Zombie process. So a zombie process is one which has completed the execution and exited via the exit system call, but there is still an entry of that process inside the process table. Orphan process. So let's say there is a parent process and that created a child process, and the parent process has finished its execution and removed from the process table, but the child process is still running. So in that case, the child process is known as the orphan process. Now we will understand how a process is created in Unix. So first way to create a process in Unix is using the fork system call. So the fork system call creates a new address space, copies all the text, data and stack section in the new address space, and provide access to open files. So initially we have one process that might have opened some files. Then we do make the fork system call. it will create another process, a copy of that process, and provide access to open files. Next way is using the exec system call process scheduling. So process scheduling is the process of scheduling a process for efficient utilization of the CPU. And there are multiple types of process scheduling. In the preemptive scheduling, what we can do is we can pause a running process, run some other high priority process, and then later continue the paused process and resume the process, and that will continue from that state. Other type of process scheduling is non-preemptive, where once you start a process, you have to wait until its execution is done. Context switching. So context switching is an important topic. So context switching is the procedure that a computer CPU follows to switch from one task to another task. So this context switching will be helpful in the case of preemptive scheduling, where we want to stop a process and start some other process in the meantime. CPU scheduling. So CPU scheduling is the process of scheduling processes that wants to use the CPU time. And the reason why we need CPU scheduling is there are blocking operation, like a process may want to read a file or make a network call or take user input. So in that case, the CPU time will be wasted. Next need is CPU time. So if a process is taking too much time to execute, other processes should not starve in that case. Parameters of CPU scheduling. So the first one is CPU burst time. So the burst time is the duration for which the process gets the CPU. So this is the actual time when the CPU is executing the instruction of that process. Second one is CPU utilization. So that is the percentage of time CPU was handling a process to the total time. So the CPU utilization shows that how many processes were executed and the CPU time was utilized in a better way or not. Waiting time. So total amount spent in the ready state. So a process might be waiting for it to get the CPU. So that time is known as the waiting time. Next is turnaround time. So that is the total amount of time when the process is submitted to the time the process is completed. So this covers the whole time from the start to the end. Throughput. So throughput is the number of processes that can be completed in a unit time. Let's say in a unit time we are executing 10 processes. So the throughput of that system will be 10. Load time, the average number of processes that are pending in the ready state. How much load is there on the CPU, that indicates the load time. Response time, so that is the interval when the process was first submitted. So that means it was in the new state, and the first time when it got the CPU. So that was the running state. So that time is known as the response time. CPU scheduling algorithm. So let's look at some of the scheduling algorithms. The first one is first come first serve. So as the name suggests, the process that comes first is assigned the CPU first. Then the second one is shortest job first, and this is the non-preemptive version. That means if we start a process, then we have to wait until it is finished. So in shortest job first, as the name suggests, any process that has the shortest time will be executing first. Now the third one is shortest job first, and this is the preemptive version. If we are executing a process and some other process comes in which has a shorter time, so that will be executing first in this case. Fourth one is priority scheduling. So we assign a priority value to each process, and based on what algorithm we are using for priority, either 10, let's say 10 is maximum priority and 0 is the minimum priority, or 0 can be the maximum priority and 10 can be the minimum. So based on that we execute the processes. Fifth one is round robin. So in round robin what we do is we maintain a queue, and in that queue we have all the processes, and we execute a process for some time quanta. Let's say we execute one process for like 10 seconds, and then we execute the other one and put it back into the queue, and we go in the round robin fashion. Interprocess communication. So interprocess communication is the way two process or multiple process communicate with each other. There are mainly two types of process. First one is the independent process. So processes operating concurrently on a system and they don't affect some other process. So in independent process, they don't need any other process for their completion, and they can execute by their own resources. Second type of processes are cooperating process. So these processes can be affected or affect some other processes. So they involve communicating with multiple processes to get their work done. Now let's understand, why do we need cooperating process at the first place? Why can't we have independent processes only? So the first reason for that is sharing information, like multiple processes might be accessing same database. So we have a central database and we are running some multiple processes, and all those processes are accessing that database. In that case we will be needing cooperating processes. Second one is computation speed up. If we can run multiple processes parallelly, that will of course increase the computation speed. Since the CPU are very powerful these days, they support parallel computation, so that will be beneficial. Third one is ease of usage. So in case of multitasking, let's say we are listening to some songs and writing some code, so in that case we can run multiple processes parallelly, so which enable the users to perform multiple tasks. Now, types of interprocess communication. First one is using the shared memory. So initially we have a memory which is within one process, and what we want to do is we want to share that piece of memory to some other processes as well. So in that case, what will happen is the process need to make a few system calls, and after making that system calls, that memory will come in shared memory. So the operating system knows that this memory is shared memory, and that way multiple processes can access that memory safely. And then there might be some other processes that need that shared memory. So what those processes have to do is make system calls again to access that shared memory, which is residing in the address space of some other process. So generally there are like a few messages passed back and forth to just set up. So that is like some acknowledgement type of a thing to coordinate between multiple processes. Other type of interprocess communication is using message passing. So in a message passing system, that system should have these two system calls, which is used for passing a message and used to receive a message. And in order to pass those messages, the processes should establish a communication link so they can share information with each other. So let's look at how a message passing system works. So there are two ways in which it can work. First one is direct communication. So in direct communication, the sender should know to whom they are sending the message. So the receiver name or some identity should be known to the sender. So what happens is we create a one-to-one link between two of the two processes, in which one is a sender and one is a receiver. And for symmetric communication, the receiver should also know the name of the sender from which it will receive the message. So there is like one-to-one link created between all the processes that want to share some information. In case of asymmetric communication, this previous step is not necessary, that receiver may or may not know the name of the sender. Second type of way is indirect communication. So in this communication, we use either a shared mailbox or some port to send and receive the message. So by default, when a process creates a mailbox, what happens is only the creator or the owner of that mailbox can read the message. All the other processes that are attached in that message passing system can only send the message to that mailbox. And note that this ownership of reading the message can be passed on to some other process, so they can read the message as well. That's how it works. So let's say process 1 is the owner and it has the read access. Then the process 1, once it is done reading the message, it can pass on the ownership to someone else. So the main advantage of indirect communication over the direct communication is that the sender doesn't know whom they are sending the message, because that is immaterial. They are directly sending to the mailbox itself. Also in this system, multiple processes can communicate with each other. Synchronization. So this is an important topic. So as we saw in the message passing system, the process of sending or receiving message can be of two types. That can be blocking, that means synchronized, or non-blocking, that means asynchronized. So blocking operation is when the sender has to wait for the receiver to receive the message. Until or unless the other receiver process doesn't receive a message, the sender cannot send message to some other process. So that is a blocking way. And the receiver operation can also be blocking if the receiver has to wait for the message to be received before either sending it or doing some other computation. Buffering. Other decision is regarding the size of receiver queue. If the receiver is not in a blocking way, so it is asynchronous, in that case we need to maintain a receiver's queue so multiple messages can be received. So we have some choices here. First one is we do not keep any queue and the sender will have to wait. So in that case, the sender will be in blocking state. Second one is we keep a bounded queue. So in a bounded queue, we have a fixed size of queue in which messages can be stored, and then the receiver can receive those messages. And in case that queue is filled up, in that case, sender will have to wait before the message is received. Third case is unbounded queue. So in this case, we don't have a limited queue size. Theoretically, the queue size of the receiver is considered to be infinite, but practically we don't have so much resources. So this approach can fail when the queue size can become pretty large. Now, as we have seen both the shared memory and message passing system for interprocess communication, now let's see what are the differences between them and when we should use which one. So shared memory is considered the faster one once the initial setup is done. The reason why it is the faster one is we do not need to make too many system calls. So once a process is connected to the shared memory, then there is no intervention of kernel where we have to make system calls. So that's why shared memory systems are faster. The drawback with shared memory systems are they are complicated to set up, and when there are multiple computers involved, they do not work very well. So the best scenario when we can use shared memory is when we have to pass large amount of data, and and that data has to be passed between two processes, and those two processes are on the same computer. So in that case, shared memory is the preferable strategy. On the other hand, the message passing system requires system call for every message. So there is a system call for sending a message and receiving a message. So every time some information has to be passed, we have to make a system call. So message passing is simple to set up and works well across multiple computers. So if your process resides on some other computer, in that case also message passing works well. And it is preferred when the amount of data that has to be transferred is small and multiple computers are involved. Threads. So this is a very important topic for interview, and let's start with it. So a thread is just a lightweight process that has its own program counter, a stack, and a set of registers. And it also has some extra information like a thread ID. So a traditional process or any normal process has a single thread, and that single thread is known as the main thread, in which all the execution happens linearly. So there is just a single program counter and one set of instruction can be carried at any given time. On the other hand, in a multi-threaded application, there are multiple threads and all those threads are inside a single process. Each thread has its own program counter, stack, and set of register, but they share a common code and the data part, and also the files that are opened by that process are also shared between all the threads. So this is how a single threaded process and multi-threaded process look like. We have the normal code, data, and files here, and we have that same in the multi-threaded process, and we have just one set of registers and a single stack. And this is the thread, which is the main thread. So this is how a single threaded process works. In case of a multi-thread process, each thread we can see has its own register and a stack. So that is how a multi-threaded process looks like. Now the question arises, why do we need threads? Why we can't work with a single threaded environment? Why do we need multiple threads? So let's try to see the reason for that. So threads are useful in a scenario when a task might block the main thread. So let's say a task want to make a network call to some API to fetch data. In that case, if we have a single thread, the execution of the main thread will block here, and as a result there can be like system hanging up or process hanging up, something like that. So that's one need for multiple threads. So this is also that same point. In case of a network call, the process can spawn another thread, and without blocking the main thread, we can execute that IO task or some other task on a separate thread. A very important use case of multi-threads is a web server. So a web server allows many requests at a single time. So it can handle multiple requests, millions of requests at a single time. So that is done by using threads. So whenever a request is made to a web server, that generally spawns a thread, and that work is completed by that thread, and the response is sent back to the user. So a little note I have written here. So like it seems that it is very easy to just simply spawn a thread and do a task, but there are some limitations to that. First of all, there are only a limited number of threads that can be created, since they need their own stack section and program counter, so they are taking up some space. And also there is some time that is required to create a thread, right? And also there can be conditions where multiple threads are accessing like a single database or a central database. In that case, it becomes tricky to handle the situation, so we don't have data corruption or corrupt or things like race condition, which we will look in the upcoming. Now let's talk about some of the advantages of threads. Threads increase the responsiveness. So since we are not blocking the main thread, as a result, the main thread can continue its execution and other threads can do the blocking task and return the result once it is completed. Resource sharing is easy. So by default, the threads, as we saw, shares a common code data and open files or some other resources like that. So if we compare that, we want to spawn a new process or we spawn a new thread. Spawning a new thread is an easier and less resource extensive way, since we do not have to copy this entire code data and some other resource section. The thread can utilize these sections of the process, so it is economic. Creating threads is much faster than creating a new process. So scalability is also an important aspect here. A single threaded process can only run on a single CPU, but since now multiple CPUs or multiple core CPU are easily accessible, so in that case, if we have a multi-threaded process, it can use those resources efficiently. Now let's look at some of the multi-threading models. So there are two types of threads that are to be managed in a modern operating system. The first one is user threads and the second one is kernel threads. So user threads, as the name suggests, are created by the application programmer. So the process spawns a thread and they do not have the special accesses that a kernel threads have. Kernel threads, on the other hand, is supported by the kernel. So most of the modern systems have kernel threads, so we can run multiple system calls simultaneously. So now let's look at some thread mapping, how the user to kernel thread mapping is done. So the first model is many to one model. As the name suggests, many user level threads are mapped onto a single thread. So these are user level threads here on the top, and they all are mapped to a single kernel thread. The main problem with this approach is that since there is a single kernel thread, so that is the bottleneck here. If the multiple user threads want to run multiple system calls, so in that case, there will be higher load on the kernel thread and the responsiveness will be less. Second model is one-to-one model. So each user thread is mapped to a separate kernel thread. As we can see, this is a user thread and each of them has a separate kernel thread. So since we create separate kernel thread for each user thread, multiple CPUs can be utilized in this case. So the efficiency of the system will be good. The problem here is that there is a lot of overhead since each user thread has their own kernel thread. So managing all those kernel thread will eventually slow the system down. Next one is many to many model. So here we have some number of user threads and some number of kernel threads. So in this mapping, the kernel threads, number of kernel threads are generally fixed and then multiple user threads are created. So this is combining both the one-to-one model and many-to-one model. Process synchronization. So this topic is very important in terms of interview. So process synchronization is how coordinating processes which share some single source of data which is shared across all the processes executes without having issues like the race condition. So we will look at what is race condition in the upcoming slides. Before looking at race conditions, we will look at what is a critical section problem. So the overall idea is that in a number of cooperating processes, each of the process has a critical section of code. And the condition is that only one process can be allowed to execute in their critical section at any one time. So the reason for that is since we have a shared resource, so multiple processes should not access that concurrently. Here we can see the code. We have an entry section, then we have the critical section, we have the exit section and remainder section. So the critical section is the one which only a single process can execute at one time. Let's talk about the entry section. So the code before the critical section which control the access to the critical section. So the entry section checks if some other process is running the code of their critical section or not, and based on that they give the access of critical section to that process. The exit section, what it does is generally releases the lock. So maybe while entering into the critical section we are putting a lock that no other process should enter the critical section, and once our work is done in the critical section, then in the exit section those locks are freed up so other process can access the critical section. Now let's look at why only one process should execute their critical section. Why not multiple or all of them at once should execute their code of the critical section? So to answer this question, we would have to learn about something known as race condition. So let's start with race condition. But race condition also has a dependency of some other problem. So first we will look at the producer consumer problem, and through that problem we will try to understand what is a race condition. So in the producer consumer problem, The producer process is producing some items, and we have another process which is a consumer process, and it is consuming those items produced by the producer. So we are mapping a memory buffer which is shared between both the producer and consumer, and that buffer is of fixed size. So the producer will produce some item and put it on that memory buffer. The consumer will pick up items from that memory buffer. Let's define the problem. So the producer process should only produce data only when the buffer is not full. In case when the buffer is full, the producer will wait until the consumer has consumed some of the process and there is some space on the buffer to put data. So the consumer can only consume items if there is at least one item on the buffer. Because if there are no items, there is nothing that has to be consumed. So it will have to wait for the producer process. So accessing the memory should not be allowed to the producer and consumer process at the same time, and we will look at why this is the case. What is the problem if they both access the memory at the same time? Let's look at some code of the producer and consumer function. So first we will look at the code of, so let's look at the producer and consumer functions. So this is the producer function. Here we have a count variable which has an initial value of 0. Then the producer function, we have an item here, and we are running an infinite loop. So inside that loop, we are producing an item here, and here we are checking if the count is equal to n. That means the buffer is full. So while the buffer is full, we can't execute this statement. So we are running a loop here for that reason. After that, we store that item on the buffer. We increase the index where the producer function is pointing in the buffer, and we increase the count. That means we have added one element. This is the consumer function. So we have a count again, and this is the consumer function, and we have item, and similarly we are running an infinite loop, and we are checking if the buffer is empty or not. So here it is checking if buffer is empty, and once the buffer has at least one item, we pull out that item here, we change the out index, and we decrease the count since we have consumed one item from the buffer. I hope the code is clear. So now let's look at the race condition. So we will try to execute some code and see what is the issue if both the producer and consumer are running their critical section code at the same time. So here we will see the race condition. So this is the code for doing count plus plus, and this one is the code for doing count minus minus. So inside the CPU we have registers, and through those registers what we do is we do multiple operations. Like here we are storing the counter value into the register 1, then increasing the value of register, and then moving the register 1 value into the counter. Similarly we are doing here in the consumer function. Now let's look at this part. So this part will explain us the race condition. Initially the producer is executing some code. So this is the code, register 1 is equal to the counter, and the value of counter initially is 5. So I'll write it down here. So this statement is done. Next up, the same producer is executing this statement. So register 1 will increment its value. That means its value becomes 6. So that is executed. Now there is a context switch here from producer to consumer. The consumer will store the value inside register 2, that is the counter value, and we can see the counter value is unchanged. It is 5 here as well. So register 2 value will be 5. Register 2 will decrease its value. So register 2 value will become 4. Now there is a context switch again. So producer is executing the code, and the counter will be equal to register 1, which was in the last iteration 6. So the counter becomes 6 here. Now the consumer again executes its last line of code, which is counter equal to register 2. So here I should change this to 6 because it was changed 6 here, and register 2 value was here 4. So now counter will become 4, but that is wrong because we have produced an item and consumed an item. So initially the counter value was 5. That means there were 5 items on the buffer. The producer produced one of the items, so it should have been 6, and then the consumer should have consumed it, so it should have been 5 again, and rather it is 4. So this is the race condition. The value of the counter is not accurate since both of these code were simultaneously executing those statements. Now let's try to look at the conditions for solution of a critical section problem. So this will help us to arrive at the solution for a critical section problem. First one is mutual exclusion. So only one process at a time can be executing their critical section code. Second is progress. So if there is no process that is currently in the critical section, some other process that is waiting for the critical section should be allowed to run code of critical section. So it should not be blocked by some other process where there is no progress. Third one is bounded waiting. So there should be a limit on how many processes can get into the critical section. That is after a process request entry into their critical section and before the request is granted. Let's look at the first solution, which is the Peterson solution. So the Peterson solution is based on two processes. Say we have a process P0 and a process P1, which alternate between their critical section and remainder sections. So we want to share some of the data items between these two processes, and those data items are, we have a turn variable of type integer and another one is an array of size 2 which is of type boolean and known as flag. So we will understand the use of these variables when we will look at the code of the solution. So the turn variable denotes whose turn it is to get into the critical section. If the turn value is equal to 1, that means process P1 is allowed to execute the critical section. And the flag array indicates that a process is ready to enter the critical section. So if flag of 0 is true, that means P0 is ready to enter the critical section. Now let's look at the code part of the Peterson solution. So this is the code, and this code we are running for the process I. So I process, I'll write here. And we have one more process called process J. So we will call that PI and PJ. So PI is executing this code. What we do is we set the flag of ith process to be true. That means the process I is ready to go into the critical section. And here we set the turn to be equal to some other process, the second process, which is not requesting the critical section. This we are doing because let's say after some time while the process PI is executing their critical section code and now PJ want to execute their code. So we are giving them a chance. If they want to execute the code after PI is done, they can do that. So that way process PJ doesn't have to starve until the PJ process is completed. So here what we are doing is we are checking if flag of J is true. That means J is in the critical section and turn is also equal to J. So this denotes that process J is PJ is executing their code in the critical section. So we should wait until they are done executing the code in the critical section. And once that is done, we enter the critical section. Once the work inside the critical section is done, we say that flag of I is equal to false. That means we are done with the critical section, and now some other process, if they want to enter the critical section, they can do that. So this is the code for the Peterson solution. Let's look at the correctness proof of Peterson solution. So first one we have to do is mutual exclusion, since we saw that in the conditions. So if one process is executing their critical section, no other process should be executing their critical section. That is true, since we are setting the flags in that way. So here we can see the flag array will stop the other process to enter the critical section. Second one was progress. So the shared variable that we had, which was turn, so that was giving the turn to process J while I was asking for the entry into the critical section. That means there is some progress. Process PI won't hold the critical section forever. So once its work is done, process PJ will be allowed to execute their code. Third one was bounded waiting. Since no process ever sets it back to their own turn, so when the process I was executing, they was setting turn as J. So this will ensure that bounded waiting is happening. Let's look at some of the problem with the Peterson solution. First one is that it works only with two processes. So we saw that we had process P0 and P1. So we cannot have more than two processes. So that is a major disadvantage. So we have a busy waiting solution. And what is meant by a busy waiting solution is that a process is constantly checking for the condition to be satisfied before its execution. So that while loop we had, which was checking the turn and the flag, that was causing busy waiting. Mutex locks, mutexes, or simply we can call it mutex. So the terminology when using mutexes is that we acquire a lock before entering the critical section, and once the work of critical section is done, we release that lock when exiting. So here we can see in the code, first we acquire a lock, then we enter the critical section, and once the critical section work is done, we release the lock. And one important thing is that the lock operations should be atomic, and atomic means that these operations are completed without any interruption. So if we start executing some operation, we won't have a middle state where either it is not done or not. We will look at what atomic means once we look at the code. So now let's look at the code of acquire and release. So in acquire, we are checking if the lock is available or not. So while the lock is not available, we just keep on looping forever here, which is a busy waiting, as we saw in the previous solution as well. And once this available becomes true, we set it to false. That means we have acquired a lock successfully. And in order to release, we just make available equal to true. So the problem here is same as Peterson solution. We have busy waiting here, and these types of lock which have busy waiting are known as spin locks. The reason why they are known as spin locks is because the CPU just waits spinning there and waiting for the lock to be released. The reason why busy waiting or spin locks are bad is it wastes CPU cycles. And if we have a single threaded machine with not much resources, that can reduce the performance. Let's look at what are the disadvantage of mutex. So the main disadvantage of the implementation of a mutex lock is that it requires busy waiting or spin locks. So in order to solve that problem, we have semaphores. So let's look at what is that. So semaphores are simply integer variables for which we have two atomic operations. First one is wait and the other one is signal, and which can be implemented in the following way. This is the wait operation where we'll check that this semaphore value is less than equal to 0. So if the semaphore value is less than equal to 0, we just keep looping on here, and once the value become positive, we subtract 1 from the semaphore value. Similarly, the signal function just increases the value of semaphore. Let's look at how we can use a semaphore. First type of semaphore that we can use is a binary semaphore. So a binary semaphore can take two values, either 0 or 1, and these are similar to mutexes since the mutex can be available or not available. Next type of semaphore is a counting semaphore. So a counting semaphore can take any integer value, and this is used to count the number of processes remaining of some limited resource. So the initial value of the semaphore in case of a counting semaphore is set to number of resources that are available in the system. So let's say if we have 10 system available, we set the value of semaphore to be 10. And the reason why we do it, we saw that in the wait function, we wait for the semaphore value to become positive. So until or unless it goes to like 9, 8 and then so forth, -1 or 0, let's say. So till then we have the available resources, so we can allow the processes to use those resources. That's why the value of semaphore initially is equal to number of resources. And whenever the counter value is greater than 0, then the process can enter the critical section, which we saw in the wait function, and can use any of the available resources. When the counter value gets to 0 or negative, then the process blocks other processes that wish to acquire the resource. That means we don't have enough resources, so the process has to wait to enter the critical section. Let's look at an example of counting semaphore. Let's say we have two processes, P1 and P2, and it is important that the P1 executes the statement S1 before P2 execute the statement S2. So how we can arrive at this solution? So I would recommend you to pause the video and try to come up with a solution if possible. So now I will start the solution. So we create a semaphore variable, let's call it sem, that is shared between both the processes, and its initial value is equal to 0. We will see why this value was equal to 0 initially. So in the process P1, what we do is, so this is the statement S1 that has to be executed before statement S2 of process P2. So what we do is we signal the semaphore, and we signal the semaphore after executing the statement S1. And we saw that initially the value of semaphore is equal to 0. In process P2, we wait for the semaphore and then we execute the statement S2. Now let me write the P1 process code. So sem value was equal to 0. Let's say process P2 tries to execute the statement S2 first. So it will come to wait, and inside wait we will see that the semaphore value was equal to 0. So we will wait for this signal code to execute, and this signal code can only execute after the statement S1 is done with its execution. So once S1 is done with the execution, we signal here. This signal will break this wait loop, and then S2 will execute. So our condition is satisfied. First S1 will execute and then S2 will execute. So that is how we can arrive at a solution using semaphore. So the implementation we just saw right now of the signal and wait function in semaphore, it was still a busy waiting solution. So we can try to tweak that solution so it becomes a non-busy waiting solution, which was our main goal to introduce semaphore. Otherwise we would have used mutexes itself. So this is the code. We have a structure called semaphore, and it has a value which is the value of semaphore, and it has one extra thing. This is a process list. So we will see how we can use this process list to remove busy waiting. In the wait function, we decrease the value of semaphore, and now if the value of semaphore becomes less than 0, we add this process to the process list, and then we block the code here. So the process stops here, so it can't continue further on. And in case of the signal function, what we do is we increase the value of semaphore and check if the value of semaphore is less than or equal to 0. If the value is less than or equal to 0, we remove a process from the process list. So that can be the process that entered first into the process list. And what we do, we take that process P and call the wake-up function. So what this wake-up function will do is it will remove this block here, and this execution can be then continued. So that is how we can use this process list, and we won't have busy waiting now. Now let's look at some problems with semaphore. So the main problem with semaphore is deadlocks. So when using a semaphore, there can be a situation when a process is waiting for some other process. So in this condition, we can see we have wait S and wait Q. So let's try to see what exactly the issue is there. So this statement is acquiring a lock on S. This is acquiring a lock on Q. Now let's say P0 wants to execute this statement. So what it wants is this Q resource, but this Q resource is taken up by process P1. So we can't continue this execution. Now let's say we can't continue the process P0. So process P1 comes in and it wants to execute the instructions. So we come to this statement, wait S, but the resource S is acquired by process P0. So now we can see we have a circular condition here. So this P1 process wants the resource S, but this is acquired by P0, and this process P0 wants a resource that is acquired by process P1. So none of the execution can be completed. So this is known as deadlock. Another problem with semaphores are starvation. So in starvation, one or more process gets blocked forever. We can take an example. In the Semaphore implementation without busy waiting, which we saw earlier, there was no way to define the add or removing a process from the process list. We just abstracted that detail. So let's say we use a first in first out queue. In this first in first out queue, all the processes will eventually get their turn. But if we would have used a last in first out, in that case there might be a possibility that if we have a process P1 here and then a process P0, so let's say process P0 starts its execution, and in the meantime another process P2 comes in, and then P0 comes in, and then P2 comes in again, and this continues forever. So in that case, what will happen is P1 here will starve, right? So that is the problem of starvation. So let's try to solve a real world problem using semaphore, which is the readers writers problem. So there are some processes which are readers, can only read the shared data. So we have a shared data, which can be a database or something else. So the readers are reading from that database. And there are some other set of processes which are writer processes, and they can change the data. So there is no limit on how many readers can access. So we can have infinite number of readers which can simultaneously read at once. But when a writer accesses the data, it has to be exclusive. That makes sense. Otherwise we will have data corruption and race conditions as we saw earlier. So let's try to look at a solution for a reader writer problem. We can create two binary semaphores and one counter variable. So we have a read count. So this read count is used by the reader process to count the number of readers that are constantly accessing the data. We have a read count mutex. So this is a semaphore, binary semaphore, which is used by the readers for controlled access to read count. So whenever we are accessing the read count, we will go through this lock. And we have a third variable, which is a read write mutex. So this read write mutex, what it will do is it will block the writers. So since only one writer at a point can change the data, so the first reader that will access the data will set the lock, and the last reader will release it. We will see how this all will work in the code. So here is the code. We have the writer function. We are running a while loop. So first what we do is we wait for RW mutex. So we want to acquire this lock. Here we can perform the critical code or the write operations, and then we release that lock here. So the writer function is pretty simple. Now in the reader function, we want to increase the reader count since a new reader has joined. So for that, we will use this lock, which is a read count mutex. So we will acquire that lock. We will increase the value of read count. And if read count is equal to 1, that means it is the first reader. So we saw that in the first reader, what we will do, we will acquire a lock over this RW mutex. After that, since we have increased the value of read count, we will release that lock. We will perform all the reading operations. Once the reading operations are done, we again acquire a lock on read count mutex to decrease the value of read count. And if the read count is equal to 0, that means it is the last reader. We will signal the read write mutex. So now let's try to understand how this whole system works. So let's say we have a reader R1 that comes in and is the first reader. So it will acquire lock over the RW mutex. So the lock here is acquired. Then again, one more process, let's say R2 comes in, and let me write the count value. So read count, and it will become 2 when there are 2 readers. And now let's say we want to write something. So there is a writer process W1 that wants to write something. But since there are already some readers which are reading from that data, we can't perform the write operation right now. So we will have to wait until or unless these both reader process are done with its work. So when they are done, they will decrease the read count value. So this read count value, let's say, will become 1 when R2 is done with its work. Then R1 is done with its work, and this will become 0. As soon as this becomes 0 here, we will send a signal to RW mutex. So this lock will be broken here, and the writer process then can acquire that lock, perform the write operations. In the meantime, there is no other process that is reading. That is how we are synchronizing both the readers and writer to solve this problem. Let's look at deadlock in detail now. So I've explained what a deadlock is. I'll do that again. So we have these two processes, P0 and P1. This acquires a lock over S. So S is now logged. We can't access it. And let's say there is a context switch and process P1 acquires lock on resource Q. So Q is also now acquired. Then there is again, let's say, a context switch here back to P0. Now P0 wants the resource Q, but this Q resource is acquired process P1. So we can't execute it further. Then let's say then P1 comes in and it wants to execute its code. So the process P1 wants this resource S, but this is acquired by process P0 and it also can't execute further. So these both processes P0 and P1 won't execute further and they are in a deadlock situation. So let's look at some of the necessary conditions for a deadlock to occur. First one is mutual exclusion. So there should be at least one resource which must be held in a non-shareable mode. So there should be a resource which is critical. So only one process can access it at a single time. Second condition is hold and wait condition. So a process must be simultaneously holding at least one resource and waiting for at least one resource that is currently being held by some other process. So in the previous example, we saw P0 was holding some resource and it wanted a resource that was available with the other process P1. So that is the hold and wait condition. Next one is there can't be any preemption. So once a process is holding a resource, then that resource cannot be taken away until or unless that process is done executing its code. Fourth condition is a circular wait. So a set of process, let's say P0 to Pn, must exist such that every Pi is waiting for Pi plus 1. So in that case, what we'll have, Pi will wait on P2, P1 will wait on P2, P2 will wait on P3, and P3 will wait for P1 again if we have 3 processes. So we have a circular condition here. So these are all the necessary conditions for a deadlock. Now we will see some methods how we can handle deadlock. First type of method is prevention from deadlock. So in this approach, what we do is we do not allow the system to get into the deadlock state. Second type of method is deadlock detection and its recovery, or preempt some resource when the system has a deadlock. So we have some deadlock detection algorithms which can detect if we have a deadlock or not, and based on that we can preempt some of the resources. So let's look at deadlock prevention strategy first. So deadlock can be prevented by preventing at least one of the 4 necessary conditions. So first one was mutual exclusion. So shared resource, let's say we have a read-only file. These read-only file won't be leading to deadlock since multiple readers can read that file without any problem. Second one is hold and wait. So hold and wait here requires that all the process requests the resource at one time. So it's not like first P0 will access, then P1 will access the resource, then P2. All of them should be acquiring the resource at the same time. So as a result, there won't be some dependency with each other requiring the same resource. Require that process holding resources must release them before requesting new resource. So if P0 is holding a resource Q and it wants to access a resource R, first it should release this queue resource before acquiring a lock on the R resource. Third condition was no preemption. So one of the approach here is, if a process is forced to wait when requesting a new resource, then all the other resources previously held by this process are implicitly released. So the similar thing, if process P0 has a resource P, Q and R and it wants to access a resource S, it will have to give up upon these resources P, Q and R. Fourth one is circular wait. So to break this condition, we can number all the resources and to require that process request resources only in strictly increasing order. So we can number the resources, let's say R1, R2, R3. So a process first will take a resource R1, then it will take R2, then it will take R3. In that case, we won't have like a circular condition where R2 was acquired first and then R1 was acquired second and so on. Banker's algorithm. So this algorithm is used for deadlock prevention and resource allocation as well. The reason why it is called Banker's algorithm is that it is used in banking system to identify whether a loan should be provided to the user or not. Characteristics of Banker's algorithm. First, if a process demands the resource, then it has to wait. And the reason why it has to wait is, since we are running the algorithm, we have to check if providing that resource will either lead to a deadlock or not. So Banker's algorithm also consists some advanced features for maximum resource allocation. Various resources are also maintained that fulfill the needs of at least one client. At least one of the process can complete its execution. And in the system, we have limited resources. So in the Banker's algorithm, if any process gets all the needed resources, then it must return the resources in a restricted period of time. So that time can be like a day long or a month long. That depends upon the program. Data structures used in Banker's algorithm. So the first data structure is available. So it is a one-dimensional array and the size of array is M. So this size determines the number of available resources of each kind. So if we have available of j, which is equal to k, so here in this case it indicates that we have k instances of the resource rj. Next data structure is max. So max is a two-dimensional array and the size of array is n cross m. So this data structure is used to determine the maximum number of resources that a process can request. So max of ij equal to k indicates that pi process can demand or request maximum of k instances of the resource type rj. So this is the process, this is the resource, and this is the maximum number of resources of type rj that can be requested. Third one is allocation. So allocation is also a two-dimensional array and the size of array is same n cross m, which is used to define the number of resources of each kind presently assigned to each process. So if we see an example, allocation of ij equal to k, this will indicate that process pi is assigned k instances of resources rj. Fourth one is need. So need is also a two-dimensional array. The size of the array is n cross m and it is used to define the remaining resources which are required for each process. So need of ij indicates that process pi presently requires k instances of resource rj. Let's look at the implementation of Banker's algorithm. So these are some of the steps. First, we check if request of I is less than the need of I. So that is like obvious. The requested number of resources should be less than the needed number of resources. Otherwise, there is an error condition and the program stops working. In step 2, we check if the requested items are less than equal to available. So if that is true, we go to the step 3. Otherwise, the process pi will have to wait for those resources to be available. Now the third step, we assume that the resources are assigned to pi since we had those resources. So we will perform the following step. We will decrease the number of available resources by the number of resources acquired by the process pi. Then we will change the number of allocated resources of process I and we will increase the number of requests. In case of need, so we will decrease the number of needed resources for the process I. So that is how Banker's algorithm can be implemented. Disadvantages of Banker's algorithm. First disadvantage is that during processing, it does not permit a process to change its maximum need. So that maximum need should be predefined. So all the processes should know in advance about the maximum number of resources needed. And sometimes it might not be possible that we know how many resources does a process need. So that is a disadvantage of Banker's algorithm. It permits the request to be provided in constrained time, but for 1 year, which is a fixed period. So we have a constrained time for which a process can acquire a resource. Next strategy is deadlock recovery. So first thing we can do is process termination. So there are two ways in which this can be done. terminate all the processes that are involved in the deadlock, or terminate process one by one until the deadlock is broken. So this is kind of an incremental approach, and this is just terminating all the processes at once, and then we restart the system. Second is resource preemption. So when preempting resources to recover from deadlock, there are three important issues that has to be addressed. First one, selecting the victim. So deciding which resource we want to preempt from which process. So that process is known as victim process. So second one is a rollback. Ideally, we want that if someone wants to roll back a preempted process to a safe state at which that resource was originally allocated. So we want a mechanism to roll back. Third one is starvation. So how do we guarantee that a process won't starve because its resources are constantly being preempted? So let's say we have a process P1 and we are given a resource R1, R2. So we preempt the resource R2, and then at some other point of time it again acquire the resource R2, and that again gets preempt. So in that case, process P1 will be starved since it is not getting that resources for enough amount of time. Memory management. So let's look at why do we need memory management. Every instruction that has to be fetched, cut that part. So every instruction we know has to be fetched from the memory before it can be executed by the CPU. And most of the instruction, what they do is they retrieve data from memory, or they write some data into the memory. So now in the modern system we have this concept of multitasking, and in that case memory management becomes an important need because we want to swap processes in and out of the CPU to the memory and maybe to the secondary memory as well in some cases. Third is also the memory is limited. So we know that we don't have infinite amount of memory in our system. However, it is quite cheap, but still we need efficient memory management to make sure that we are using that memory efficiently. Some important points about memory. So memory hardware doesn't know what a particular part of memory is being used for, and it doesn't even care. So that makes sense. The hardware should not care about what is inside the memory. CPU can only directly access the registers and the main memory. It cannot access the secondary memory. So stuff like a hard drive or pen drive, something like that, it cannot access that directly. So memory access to registers are very fast. So user processes must be restricted only to access the memory location that belongs to that particular process. So it should not touch any illegal memory that is out of its restriction. Memory access to main memory is comparatively slow. So registers one was very fast, and then main memory it's very slow. That is why modern CPUs have caches built into it. So the idea of cache is to have a very fast access by storing some of the frequently used data in the cache. So we don't have to access the main memory again and again, which can lead into a performance loss. Logical and physical address space. So the address generated by the CPU. So CPU generates a logical address, which is also known as a virtual address. Whereas the address actually seen by the memory hardware. So we have some hardware and let's say the memory that we want to access at some address 0xab or something like that. So that address is known as physical address. So addresses that are bound at the compile time or the load time have identical logical and physical address. In that case, logical and physical address are the same. And the addresses that are bound at runtime have different logical and memory address. So the memory management unit, also known as MMU, handles this mapping of logical to physical address. Swapping. So a process has to be loaded into main memory for execution. We know that. If there is not enough memory available, let's say, to run that process, then some other process which is not currently running in the CPU, we can swap that out into the secondary memory. Or maybe we have a fast local disk, also known as a backing store. We swap the memory of that process which is not currently using the CPU, so we can run some other process. Memory allocation. So one way of allocating contiguous memory is to divide the memory into equal size partition and then assign each process to their own partition. So we have a memory and then we can cut into some part of some size, let's say 10 MB or something like that, and then we can assign each process to their own partition. So there is some problems with the above approach. The problem is that it restricts both the number of simultaneous process and the maximum size of each process. So if there is a process that is more than 10 MB, we can't use this approach. Another way is to keep a list of unused memory blocks and find a block that is suitable for the size. So there are some memory allocation strategy which is using the contiguous memory. First strategy is first fit. So in first fit, we find the first big enough block to satisfy the process memory request. Second one is best fit. So as the name suggests, allocate the smallest block that is big enough to satisfy the request. Third is worst fit. So in that we allocate the largest block available. Now let's look at fragmentation. So fragmentation occurs when the processes are loaded and swapped out of the memory. As a result, the free space doesn't remain contiguous. So this brings a problem that even if we have like 10 MB of free space, but the 10 MB of free space is not available as a contiguous free space. So we can't allocate a process into that discontinuous memory. Types of fragmentation. So first type of fragmentation is an external fragmentation. All the memory allocation strategy which we saw earlier, first fit, best fit and worst fit, suffers from this fragmentation, especially the first and the best fit. So it means that the available memory is broken up into loads of smaller pieces, none of which is big enough to satisfy the next memory requirement. Even the total sum, if we calculate, is equal to or greater than the memory needed. Second type of fragmentation is internal fragmentation. So this is caused by the fact that memory is allocated in a fixed size block, whereas the actual memory needed will rarely be that exact size. So there are chunks of unallocated memory which causes internal fragmentation. So one strategy to solve the problem of fragmentation is compaction. So if the program in the memory are reallocatable, so that is an important thing. The programs should be reallocatable. Then only we can use this strategy. So then the external fragmentation problem can be reduced using compaction. So compaction is the process of moving all the processes down to the end of the physical memory. So this is the memory we have. We have a process P1 aligned here. Then we have a free memory block, P2, free memory block, P3 and free memory block. So after compaction, we can see all these processes are stacked here and the free memory is available here. So now if some process comes that is like big enough to fit in here, we can actually do that. But before that we couldn't do it because the memory was not contiguous. So compaction helps solving fragmentation in some cases. Segmentation. So segmentation is also a memory management technique in which we divide the memory into some variable size parts. So details about each those segments are stored in a table known as the segment table. So segment table contains mainly two information about a segment. The first one is base, which is the base address of the segment, and second is the limit. That means how much memory can that segment store. Disadvantages of segmentation. So it can have external fragmentation. So difficult to allocate contiguous memory to a variable size partition. So in order to solve the problems of segmentation, we have paging. So paging is also a memory management technique which allows processes physical memory address to be discontinuous to eliminate the fragmentation issue. So let's see how we can do that. The memory is allocated in equal sized blocks which are known as pages. So the memory is allocated in pages. So we have to keep that in mind. So it is one of the predominant memory management techniques which is still used in modern systems. Let's see how paging works. So the basic idea behind paging is we divide the physical memory into a number of equal sized blocks. So those equal sized blocks are known as frames. So the physical memory is divided into frames and the program's logical memory. So the program's logical memory space is divided into the same block of same size, which is known as pages. So this is our physical memory, which is divided into some blocks known as frames. So these are frames. We have a page table, which is used to store the information about what frame a particular page is stored in. So if we have, this is the CPU and this is the logical address. So we have a page and this is the offset. So using this information, we can locate this page in the page table, and from the page table we can convert it into the physical address. Since the page table stores that information, once we have the physical address, we can find that process in the physical memory here. So it is available here, which is F, right? So that is how paging works. So a logical address contains two parts, a page number, which is the address, and we have an offset from the beginning of the page. And the page table maps the page number to a frame number. So this is the frame number, and the physical address similarly has two parts. One of that is frame number and other one is offset. So there is no external fragmentation with paging. All blocks of physical memory are used and there are no gaps in between and no problems with finding the right size hole for a particular chunk of memory. So there is, however, internal fragmentation. So memory is allocated in chunks the size of a page, and on an average the last page will only be half full. So that will waste some memory. So we will have internal fragmentation in that case. Speeding up paging. So let's see how we can speed up paging. Page lookups must be done for every memory reference, and whenever a process gets swapped out from the CPU or in the CPU, its page table must be swapped out too, along with the instruction registers and some other data as well. So it is therefore appropriate to provide hardware support for this operation. So that will make it as fast as possible, and to make process switches as fast as possible as well. So an alternate option is to store the page table in main memory and use a single register. So we can use a single register which is known as page table base register, PTBR, to record where in the memory the page table is allocated. So this PTBR will store that where in the memory the page table is located. So this will make the process of switching fast, since only a single register needs to be changed. So we will change it here rather than reallocating everything. But the main memory just got half as fast because each memory access now required two memory accesses. So one will be to fetch the frame number. So that will be right here, one memory access, and then other two access desired memory location. So other will be this accessing it right here, second. So we still need two memory accesses. So the solution to this problem is to use a very high speed memory device, which is known as translation look aside buffer, or TLB. So the TLB will act as a cache. If we find the address in TLB, which is a TLB hit, we can directly access it. If we do not find the address in the TLB, it will be a TLB miss, and we would have to look in the page table and simultaneously store it in the TLB and access the address. So what that means is, first we check the TLB. If we have the required information, we simply go here and access the memory that we want. If we do not get that data in TLB, we have a TLB miss, we access the page table, and then we store that entry inside the TLB, and simultaneously we also access that memory in the physical memory. So that is how TLB works. So since TLB is a small memory, so we need a strategy like least recently used, or LRU, to evict the item. So we have to decide which items to keep inside the TLB and which items we have to remove. So for that we can use some strategy like LRU. Now let's look at virtual memory. So the need for virtual memory arises because in techniques like paging, as we saw in the previous slides, and segmentation, we still want the whole process to be in the memory for execution. But in practice, most real processes do not need all their pages, or at least not all at once. So what we can do, we can load some pages, and as the process demands some other pages, we load those lazily. So reasons for this is, error handling code is not needed unless some error occurs, and some of the errors might have a very low chance to occur. So loading those doesn't make any sense. Arrays are often oversized, so that is for the worst case scenario, and only a small fraction of the array is actually used in practice. Certain features of a program are rarely used, so it doesn't make any sense to keep that in main memory. And this process of loading pages when they are actually required is known as lazy loading. So let's look at the benefits of virtual memory. First one is, programs can be written for a much larger address space than physically exist on the computer. So this is true that maybe we have 8 gigs of RAM and we are playing a game which is requiring like 10 gigs of RAM to load it completely. So what virtual memory does is, it allows this to break up, and as a result we can load only some parts inside the main memory that are needed at that particular time. Next benefit of having virtual memory is more memory left for other programs. As a result, it improves the CPU utilization and system throughput. So what this means is, if we have this game of 10 GB and we are loading only 4 gigabytes, maybe we are running some other programs like any music in the background. So there will be space left for that to be loaded and played. File system. So a file system is the method and data structure that an operating system uses to keep track of the files or a partition. File attributes. So these are some of the attributes of a file: name, extension. Like in Windows, we have some game.exe, which is an executable file. So this is the name and extension. Identifier. So for example, in Linux, we have a inode number. So an inode number is given to a particular inode. So inode is a data structure in Unix operating system that contains important information pertaining to files within a file system. Type of the file. So it can be a binary, executable, or simply a text file. Location. So that is the location on the drive. Size of that file. Permissions, like a file might be read only, so you can't write anything on that file. Time and date. So there are things like last modified date or when the file was created. So created date. Owner. So who is the owner of that file? Like root can be owner of a particular file, or some other user in the system can be owner of that file. Access methods. So first type of access methods on file is sequential access. So generally in CD DVDs we have this kind of access where we have a read write head which moves around on that CD or DVD to access the data sequentially. Second one is direct access. So in direct access we can jump to any record and read that record directly. We do not have to trace the whole part before the address that we want to access. So a hard drive is a good example of that. Third way is index access. Very large files may require a multi-tiered index system. So that is like an indexes of indexes. So here indexes of indexes can be, we have a higher level index here, and which is pointing to some other table which is storing some indexes, and then this is pointing to a file or a data somewhere. So these are multi-tiered indexing. Let's look at a directory structure. First one is a storage structure. So a physical disk can be broken up into multiple partitions, slices, or mini disks, each of which can become a virtual disk and can have its own file system. Like we have C drive for Windows and D drive for your homework folder. We all know that. Or multiple physical disks can be combined into one large volume. So we can have multiple disks and that can act as a single disk. So this here is file system of Linux. So we have a root directory. So it is like a tree like structure. We have on the top we have root, then we have /bin which have some executables, /opt, boot, and so on. Let's look at some of the directory structures. So very common one that is used is acyclic graph directories. So when the same files need to be accessed in more than one place, maybe they are being shared or we have a copy of that somewhere else in another folder, it can be useful to provide an acyclic graph structure. So Unix provides two types of links for implementing acyclic graph structure. First one is a hard link, which involves multiple directory entries that refer both to the same file. Second type is a symbolic link, or it is also known as symlink. So it involves a special file. So symlink is a special file that contains information about where to find the actual file on the disk. So we can see here an acyclic graph directory. This is like the root folder and we are pointing to this folder, and these are files. So we can see the count here and here in dict and spell is pointing to some same file. So that is possible in acyclic graph directories. So file system mounting. The basic idea behind mounting file system is to combine multiple files into one large tree structure. So the mount command is given a file system to mount and a mount point. That means where we want to attach that particular file system. So any files or subdirectories that had been stored in the mount point directory prior to the mounting, the new file system are now hidden by the mounted file system and are no longer available. For this reason, some system only allow mounting onto the empty directories, because that can cause loss of data if we are mounting to some directory where we have some other stuff. Let's look at an example of file system mounting. So we have this file system. So this is the root and we have some other folders and subdirectories. So this is the file system that we want to mount onto this one. And we say that we want to mount this file system, this one that we have, under users. So under users, we want to mount this. So now we can see under users, we have Sue, Jane here, and this part is now overridden by this file system. So this is how mounting works.